Well, firstly, I'd like to thank all of you for being here today. May I present our team, the HCMUS team approaches for the medical task in MediaEval 2020. This is the outline of our presentation, and we shall start with the overview. The task is to segment different types of polyps that requires high accuracy and time efficiency. So there are 1,000 images for training and 160 for evaluation. Task 1 is scored with Jaccard index and task 2 with frames per second and Jaccard index. In our first approach, we applied PraNet with ResUnet 50 backbone. The training dataset mostly contains simple samples where polyps are easily recognized. Only a few harder samples with small, flat, or irregular polyps. We applied the training signal annealing method to prevent the models from overfitting on simple cases and force them to penalize on harder cases. Based on the practical situation of the colonoscopy examinations, cameras may capture the polyps from any angle. We applied random rotation as well as high boost filtering to augment the data. With the training signal annealing strategy, at each training iteration, images with a high score over a threshold are weighted less in the backpropagation process. The threshold value that gives us the best performance is given by this formula, where big T is the total number of training steps, and sub T is the threshold at step T, and K is Q. To increase the surface texture, we use high boost filtering for augmentation. It enhances the high-frequency signals and keeps low-frequency components. For example, the original image is on the left and the modified one is on the right. Our second proposed approach, we use ResUnet++ as backbone with triple input path, the orange shaded region, where we create two different enhanced versions of the given image and concat them all together as a single input for our model. We also add a layer to predict the guided distance map, the green shaded region, that predict the pixels distance to the polyps core, forcing the model to learn the shapes and size of the polyps. So, for a closer view of these two parts of our model, the two methods used for enhancing the input image are CLA, HE, and equalize transform. This step help the model to learn the multi-view input. Because these polyps images often suffer from weak boundary problem, we decide to add more weights for the pixels closer to the polyps core. That is, we assume that the closer the pixels are to the core, the more important and easier to recognize they should be. For the distance map, we just add a new layer to predict the map before getting the final result. For task 1, we submitted 5 runs, and here are our methods for each of them. Run 3 wins our best performance for task 1. It is an example of our two approaches. This suggests that each of our proposed approach has their own strength, and also our Run 3 wins the best performance overall, with Jaccard index of 0.777,365 and highest accuracy and precision. For the second task, we submitted 2 runs without using any examples to evaluate the time performance, and this is the respective result of each of our runs, where run 1 wins the first positions in this task overall. So for an examples of our results, these are the best cases where we can call it regular cases. And the worst cases of our performance is on the tiny polyps or flat polyps with unseen texture. So to sum up, the Polyps segmentation task suffer from weak boundary problem, varied polyps shapes and size problem, and the unequal distribution of the hard versus easy cases between training and testing dataset. We propose 2 models based on either PraNet or ResUnet++. Each tackles the problems differently. The first, the PraNet-based one, used signal annealing and high boost filtering. The ResUnet++ one focused more on developing the model, adds multi-view triple path inputs, and pixel-based distance map prediction before getting the final results. As the experiment suggests, they each has their own strength, and this is why we shall develop a new version leveraging them both in the near future. I guess this is the end of our presentation. Thank you for listening.